Assalamualaikum and hi. Today we are going to learn more about the elements of thermal design that comprises of heat transfer, the elements of fluid mechanics, and the elements of thermodynamics. In this lesson number 8, we will start with the heat transfer area. Upon completion of this lesson, students will be able to understand the concept of heat and heat transfer in thermal design. Second is to distinguish the three modes of heat transfer in thermal design. The concept of heat is somewhat mysterious. We talk of heat as though it is a substance. A substance is a particular kind of matter with uniform properties. Even the phrase heat transfer itself implies that something is being moved from one place to another. Through the 18th century, heat was thought to be a colorless, odorless, and weightless fluid. It is from this era that the concept of caloric theory is used. From this concept, heat is some sort of fluid that flows from one object to another. Then, as they evolved in the middle of 19th century, as the technology evolved, it was later discovered that heat is simply a form of energy called thermal energy and is not a fluid. However, a modern terminology or a modern definition of heat is energy that is spontaneously transferred from a high temperature system to a lower temperature system. The terminology of heat flow was already in common use up until now and could not be changed. Heat transfer is a large and important mechanical engineering topic that most engineering courses have at least one required course in it. When two objects at a different temperature come into thermal contact, they will exchange thermal energy, which is heat. The hotter object spontaneously gives thermal energy or heat to the colder body until their temperatures are equal, at which point they are said to be in a state of thermal equilibrium. For example here, if you leave a spoon in a cup of coffee, what will happen? In this case, hotter object, the hot coffee in this cup, gives heat or transfer its heat to the colder body of the spoon until their temperature are equal. If two systems are at the same temperature, they are said to be in thermal equilibrium, meaning they are having thermal balance or stability. There are no further flow of heat if the systems have reached thermal equilibrium state. The amount of heat transfer or thermal energy of a system undergoes a process from one equilibrium state or balanced state to another can be determined through heat transfer rate equations. In engineering, heat transfer refers to the thermal energy that passes between objects by either thermal conduction, thermal convection, in which a fluid here is either a liquid or a gas, moves between regions of different temperature, or thermal radiation, in which energy is transmitted by electromagnetic radiation. These three heat transfers modes or types are shown in this figure and will be briefly described next. As mentioned just now, there are three different modes by which heat transfer or thermal energy is accomplished, meaning there are three types of how heat is transferred from one system to another system. First is thermal conduction. Thermal conduction is where the heat is transferred from one molecule to the molecule situated next, which is in contact. Molecule is a group of two or more atoms held together by chemical bonds. For example, like this pen here. There are molecules at every single spaces in this pen system, including the handle. So when the pen is being heated, the molecules within the system will vibrate to indicate that the energy or heat is transferred. In this case, only heat or energy will be transferred, not the vibrating molecules, meaning the vibrating molecules will stay put, which is why this mode of heat transfer can only occur in continuous and rigid medium only, which is solid. Second is transfer of heat by thermal convection mode. The heat is transferred due to the molecules that actually moves from one point to another point for transferring of heat, like the molecules in this water. The water molecules at the bottom area of this pen will experience heat of energy first when being heated. As the heat energy increases to boil the water, the molecules at the bottom of the pan will move, circulate to the other areas in this pan. The medium in which heat is transferred by the movement of these molecules takes place in the continuous medium, like fluid. Fluid is either in liquid or gas. There is no need for any medium for transfer of heat by thermal radiation, since it can happen in space. The energy to start with from this fire source will be converted into electromagnetic waves. These waves will travel to any point through wave motion at very high speed. The basic equation for the rate of steady conduction heat transfer is called as Fourier's law of conduction. For steady conduction heat transfer through a plate or a plane wall, look at this figure. Fourier's law is like this equation, where the Q-con, Q-C-O-N-D, denoted as Q-con, is the conduction heat transfer rate. KT here is the thermal conductivity of the material, while A here is the cross-sectional area perpendicular to the heat transfer direction. And this symbol of triangle X here is called as delta X, is the thickness of the plate or wall. For the thermal conductivity of the material, the KT, the thermal conductivity, the value of thermal conductivity can be found in this table that is following the standard value, meaning the value of thermal conductivity of the material is constant according to the types of material used. For example of materials that we have here is like thermal conductivity of the material. Here is like liquid water, the mercury, the aluminium, copper, carbon steel, and so on. Convective heat transfer occurs whenever an object is either hotter or colder than a surrounding fluid. Convection occurs only in a moving liquid or a gas, never in a solid. The basic equation for the rate of convection heat transfer is known as Newton's law of cooling. Like in this equation, where the Q con or the QCONV is the convective heat transfer rate. H here is the convective heat transfer coefficient. If the thermal conduction, the KT is constant, for thermal convection, H is constant. So H is the convective heat transfer coefficient, a constant value. A is the surface area of the object being cooled or heated. T infinity is the bulk temperature of the surrounding fluid. And Ts is the surface temperature of the object. There are two types of convection. We have natural convection and forced convection. Natural convection is produced by density differences in a fluid due to temperature differences, for example, as in hot air rises. We will look at the example later. Global atmospheric circulation and local weather phenomena, including wind, are due to convective heat transfer. While in forced convection, the fluid motion is generated by a source like a pump or a fan. It is one of the main forms of heat transfer used by engineers because large amounts of thermal energy can be transported efficiently. It is used in heating and air conditioning systems, electronics cooling, and numerous other technologies. These figures illustrate natural convection around a hot object. The natural convection around a hot object, where it caused by the temperature of the surrounding that hits maybe these hot object surfaces. And then we have the figure of example for forced convection, which is used in designing heat exchangers in which one fluid stream is used to heat or cool another fluid stream, like a flat plate here being cooled by forced convection from this fan. This table provides values for the convection heat transfer coefficient, which is the H value, convective heat transfer coefficient, H value, under various conditions, whether it is in a condition of boiling water situation or in a condensing water vapor. All electromagnetic radiation can be considered as radiation transfer, like infrared, ultraviolet, visible light, radio, and television waves, like microwaves, X-rays, gamma rays, and so on, are all forms of radiation transfer. If an object with a surface temperature, Ts, is emitting or receiving thermal radiating energy to or from its surroundings at temperature T infinity, the bulk temperature, then the rate of thermal radiation is expressed by the Stefan-Boltzmann law of radiation, like in this equation, where Q rad or Q radian RAD is the radiation heat transfer rate. This is the symbol named as epsilon. So this epsilon symbol is the dimensionless emissivity or absorptivity. The hotter object is said to emit energy, while the colder object absorbs energy of the object. A is the surface area of the object, and the symbol of sigma here is the Stefan-Boltzmann constant. This figure illustrates how solar radiation can be used to heat water for household use, and the table lists the thermal emissivity values for various materials. So now for thermal radiation, the epsilon means the dimensionless emissivity is constant. So that's for now. In this lesson, the definition or the introduction of what is heat and what is heat transfer have been completed. The elements of thermal design principle that cover the heat transfer area are already known. For the next lesson, we will continue to discover the elements of fluid mechanics in thermal design. Thank you and Assalamualaikum.